Bismillah ar-Rahman ar-Rahim. Now we'll continue dealing with such problems in 4.1 and 4.2. Um, we deal with the first part, which is what we mean by R3. Also, this can be extended to Rn, how to add two vectors, how to multiply two vectors. And then we talk about mainly linear independence when we say two functions or two vectors or three vectors or are linear independent. So either we do it through this, find A and B. If A and B, if the only solution that A is equal to B is equal to 0, that means they are linearly independent. If I can find A and B not both 0, then they are linearly dependent. And also, with this, I have this idea how to say a vector is a linear combination with other vectors. I can find A, B, AU and B, A and B, such that AU plus BB is equal to W. And this can be extended to R3. So now I need to find A, B, C. If they are all zeros, then they're linearly independent. If at least one of them is not zero, then they are linearly dependent. Also, I can use the determinant to do that. Not only that, if they are linearly independent and they have three vectors, 3 in R3, 4 in R4, and so on. 3 in R3 are linearly independent, then they will constitute a basis for R3. This is what we did. We did some problems related to that. Yeah. Now we'll move to the idea of subspaces. What's the idea of subspaces? If you have non-empty subset of R3, we call it subspace of R3. In R3, if I have a collection of elements, I put it in a subset. This subset is non-empty. And then if I have a collection of these elements, we call it, I mean, it's a subset for sure. We call it subspace of R3 when V itself is a vector space. But for sure, we cannot check all of these 10 conditions. So we need to check only 2 conditions. Is V is non-empty? They are closed under addition and closed under scalar multiplication. So what I will do, I will take 2 vectors in that subset and see if I add these 2 vectors, am I still in the same set or not? And the same thing, if I take a generic vector, multiply by a constant, and see if C times that vector will make mistake. If C times U means that I am still in the subset or not. That's mainly the closure under addition, closure under scalar multiplication. It can be actually the same definition can be applied for Rn, not only for R2. And this is what they did in 4.1. They talk only about R2, R3. In 4.2, they talk only about R4. The same idea. So now we want to be sure about one thing. Now to prove that a subspace means I need to show for any vectors, U and V, these 2 conditions satisfied. If U and V are vectors in V, then U plus V is also in V. If U is a vector in V and C is a scalar, then CU is in V. Okay? Now, to prove it's subspace, I need to prove it for any vector. To prove it's not a subspace, I need only one example, which contradict either the first condition or the second condition. I need only one example. Okay, let me do the examples now. Yeah, this one said show that the set. Yeah, for sure. In the exam, we will not tell the show that. Then he said, I have the set V X Y Z such that such that with this one Y equal X. So I have this collection of set, which is all the elements, all Yeah, all the elements where the first component and the second component are the same. I collected. Is this collection of elements a subspace of R3 or not? It is a subspace. This is a subspace. So as I said, to show it's a subspace, you cannot do it with examples. You should not do it with example. You need to do it with a general vectors. So I let U equal x1, yeah, x1, y1, z1. And let v x2, y2, z2. Okay, U belongs to V and V belongs to V. Okay. If U belongs to V, it means satisfy this condition. Means the second component is equal to the first component. If V belongs to V, means satisfy the condition. Second component equal the first component. Okay. Now the question is U, this is the first one, first condition, is U plus V belongs to capital V or not? That's the question. So what I will do, I will see what is U plus V. U plus V is what? X1, I just add it. That will be what? X1 plus X2, Y1 plus Y2, Z1 plus Z2. Z1 plus Z2. Okay. Now the question is how to check this is in this subset or not. I'll check the second component. Is it the same as the first component or not? Are they equal or not? This is the way to say this element, which is U plus V, which is represented this way, is in this set or not. I need second component to be equal to the first component. So I check Y1 plus Y2 is equal what? Since Y1 is equal to X1, so that is equal to X1. Since Y2 is equal to X2, so this is correct. So U plus V belongs to V. Now I check the second thing. Is C times U for any C belongs to V or not? What I will do, I will find CU. What is CU? It will be CX1, CX2, CZ, CY1, CZ1. This is the CU. Now we need to check the second component. Is it the same as the first component or not? Check CY1. Oh, I know that Y1 is equal to X1. So this is equal to CX1. So this is true. It means هنا means U plus V belongs to capital V. Here means CU belongs to V. Now, look, I'm not taking a specific vector in general. I'm talking about it in general. I not take specific numbers. Huh? So that means is this and this satisfied right away. V is a subspace of R3 since I am in R3. Okay. Now check this one. He said it's not a subspace. To show it's not a subspace, you need only one example. One example. So I need now to deal with examples. I let you, yeah, I need to take, what is V? Let me write the V in this format. Says that X plus Y is equal to 1. Okay. So now I need to show it's not subspace. And it means I need to take examples where I have two vectors. I add them. They are not in the subset, the new vector, or I multiply it by a constant. Yeah, let u, for example, 1 and 0. For sure, this is in the set, since I have 1 plus 0 is equal to 1. So this belongs to V. And let V 0 and 1. For sure, this belongs to V. Now, let me check U plus V. That will be what? 1 to 1. 1 and 1. Is it in this set? No. This does not belong to V. Right away. V is not a subspace. I don't need to do anything else. I need only one example. I need only one example to show it's not a subspace. Yeah, actually, this one is very, you can find a lot of examples. And if I multiply by 2, 0 is not in the subspace, and so on. Yeah. Show that this set is not a subspace, y equal 1. Okay. So what is the set? The set will be L, X, Y, and Z, such that y is equal to 1. So always the element in the component in the middle, or the y component, is equal to 1. Is not the subspace. I need example. Let u, no, sorry, this should be 1, 0, and 2. This is 0, 1. It should be in R3. Yeah. Not make a big difference. And make it 3 or anything. The thing is here, since I need the first and the condition is about the first and second component. So this will be 1, 1, 5. Yeah, I'm in R3, not in R2. Yeah, okay. So I took U where y is equal to 1. I took anything, 0, 1, 5. Who cares? This belongs to V. Take another vector, 3, 1, 2. This is also in V, since this is 1, this is 1. Satisfy the condition. Now check U plus V. It will be what? 3, 2, 7. Now this is not in V, and this is 2. This does not belong to V. So V is not a subspace. This is the way to do it. Also in 4.2. 4.2, just he moved to R4, to Rn. The same idea, exactly. Let me be the set that this is V a subspace. Now the question is V a subspace, not show it's subspace. Yeah, is it subspace or it's not subspace? X equals 3y. Yeah, what do you think? Okay. I think it's subspace. So what is the V? If I want to rewrite it, it will be X, Y, Z, such that X equals 3y. This is the set. I mean, the first component is equal 3 times the second component. This is the collection of, this is the set, or the collection of elements. Okay, I think it is subspace. Let me try to prove it. The same thing. To prove it, I need to do it for any u and v. Let u equal x1, y1, z1 belongs to v. That means what? X1 is 3, y1. Let v x2, y2, z2 belongs to v. That means what? X2 equals 3, y2. Now I check, is u plus v belongs to v or not? So I check u plus v. It will be what? X1 plus x2, y1 plus y2, z1 plus z2. This belongs to v. When it will belongs to v, I need to check the first component, is it equal to the 3 times the second component or not? This is the question. So we'll start with the first component. We have x1 plus x2. And x1 is what? Using this condition. It will be 3y1, x2, 3y2. I can take 3 as a common factor. So this is true. So u plus v belongs to the capital V, to the subset. So this condition is okay. I need to check the second one. That's not enough. Cu plus v. Take Cu. What is Cu? It will be Cx1, Cx2, Cx3. No, I'm using y1, y2. Cy1. What is Cy1? Cz1. I need to check. Check. This one, the first component, equal 3, second component. This is the question. So we'll start with the first component. I know x1 is 3y1. So that will be c times 3y1, which is, I can deal with it this way. So this is true. So that means cu belongs to v for any c. That means what? V is a subspace. Yeah. Okay. Let me be the set x plus 3y equal 1. So this is my set. All x, y, and z. So that the first component plus the second component is always equal to 1. Is this correct? Always? Yeah. Since I do the examples before, it's not a subspace. Using the sum, let me do this example using the scalar multiplication. But actually, you can do both in this example. But sometimes one condition is okay, the second one is not. Still, this is not a subspace. So let u will be 102. Okay, then this is belongs to V. However, check 2u. 2u will be what? 204. This does not belong to V. Since this, note here, 1 plus 3 times 0 is equal to 1. So it's there. But this is 2 plus 3 times 0 is not equal to 1. So this is not. So V is not a subspace. That's mainly the idea. Just you need to do examples to show that it's subspace or not. Okay. Y square equals Z square. Is this a subspace or not? Y square is equal to Z square. Okay. I need the second component square is equal to the third component square. So V x, y, z, so that y square equals z square. I need example. I think it's not subspace. But let you think about examples. Yeah, maybe I can deal with 1 and minus 1 so that they will kill each other. So that I don't keep the square. Okay, so let u equal, for example, yeah, 0, 1, minus 1. Let v, this is belongs to, for sure, this is belongs to v, huh? Since 1 square is equal minus 1 square. So this is true. I have y square, and this one. V, I'll make it the other way, 0 minus 1, 1. This belongs to V. Since minus 1 square is equal to 1 square. This is true. Now u plus V will be what? 0, 0, 0. This does not belong to V. No, still it belongs to V. No, no. Yeah, this is not the right example. No, make it one. Sorry, make it one. Still, this is there. Yeah, sometimes to be careful. To be careful about the example. Look, the example I did, it was I mean satisfying the condition. No, you need to look at the example where it's not satisfying the condition. Yes, now it will not. U plus V will be what? 0, 2, 0. This does not belong to me. Since 2 square does not equal 0 square. So that means V is not a subspace. Okay. Show that this is a subspace. You said show that. It means you need to prove it. So you can write it this way, write it as a row vector or column vector. It's okay. Now, this is my set. So I let U belongs to W. That means what? If you look at let me rewrite this set as what? W will be all elements X, Y, Z, so that the second element is always 0. And this is a subspace. How to prove it? As we did before, let U X1, Y1, Z1 belongs to W. That means what? The second component is 0. Let V X2, Y2, Z2 belongs to W. That means the second component, which is Y2, is equal to 0. Now we need to check, is U plus V belongs to W or not? So I check U plus V, X1 plus X2, Y1 plus Y2, Z1 plus Z2. Yeah. Now, how to say this belongs to W or not? I need to check this component. Is it satisfying this condition or not? The second component, is it 0 or not? The question is Y1 plus Y2 equal to 0? Check. Y1 plus Y2, Y1 is 0, Y2 is 0, so their sum is 0, so this is correct. So U plus V belongs to W. Now the second question is CU belongs to W? The answer is yes, because CU is what? CX1, CY1, CZ1. The question is CY1 equal to 0? Yes. That's the question. Check CY1 will be C times 0, which is 0. So this is correct. So that means CU belongs to W. That means W is a subspace. Now, show that this is not a subspace? I think we did it before. No. Now, what is W? You can rewrite it, all X, Y, Z, so that the third component is equal to 1. Actually, we did it with Y equal 1, which is the same idea. Yeah, the same idea, exactly. So choose any. It is not a subspace. So this is not a subspace. Why I let let me do it with the scalar this time. U equal 0, 1, 1. So it will be 2U. This belongs to W. However, 2U, which is 0, 2, 2, this does not belong to W because this is not 1. I need the third component to be 1. This does not belong to W. So W is not a subspace. show that the set is a subspace. 0. I think we did it before. X equals 0. Yeah, we did it with y equals 0. It will be the same idea. Yeah. Let me show it. It should be the same idea, but yeah. I need to let u generic one, x1. What is the set? Let me write the set. The set is saying v, all the these elements where the first component is 0. So now I let general one belongs to v. That means the first component is 0. Let another one belongs to v. That means the first component is 0 also. The question is u plus v belongs to v? This is the first question. I check u plus v. It will be x1 plus x2, y1 plus y2, z1 plus z2. I know I have this. Okay. So the question is this in v? How to check? I need to check the first component. Is it 0 or not? And this is true since x1 plus x2 is 0 plus 0. I know x1 is 0, x2 equals 0. So that will be 0. So that means u plus v belongs to capital V. Second question is cu belongs to v, which is correct. Cu will be what? Cx1, Cx2, Cy1. Yeah, I can write the vector in general in different ways. So the question is Cx1 equal to 0? And that's true since x1 equals c times 0, which is 0. So this is correct. So Cu belongs to V. So that means V is a subspace. Yeah, I'm writing it in details, which is good. Now determine whether the given vectors are linear independent or independent. Yeah. This one is now we're doing I think now we are done with this with the explanation. Actually, what happens in R3 can be extended to R4. So I'll do these because these two questions, they are related to the first part which we did before. So I will do it later. Now let me concentrate with the subspace questions. Now you want me to do this? Determine whether I will leave these two. I will postpone them to the maybe to the next video, which I will take them as example. These are related to the first part. Okay. Determine whether the following set is or is not a subspace. Yeah. What is the first one? The first one is I need the third component to be the sum of the first two. And this is subspace. So I need to show it. So let's u, which is x1, y1, z1, belongs to w. That means what? The third component is equal to the first component plus the second component. And let another v, general one, x2, y2, z2 belongs to w. That means z2 is x2 plus y2. Okay, the question is u plus v belongs to w? So I need to check u plus v. What is u plus v? x1 plus x2, y1 plus y2, z1 plus z2. I need to check the third component. The question is the third component here the same as the first plus the second? Yes, it's true. Why? Let me start with the first component, z1 plus z2. I know z1 is this is y1, sorry. Y1 is x1 plus y1, z2 x2 plus y2, which I can rewrite it x1 plus x2 plus y1 plus y2 since I'm in R3. So it means this is true. So u plus v belongs to w. The same thing is cu belongs to w. I check cu. What will you cx1, cx2, cx, not cx, cy1. Sorry, I'm used to do x1, x2. Okay, cz1. I need to check the third component. Is it equal the first component plus the second component? Yeah, this is what I want to check. So that's true, since cz1, z1 is what? x1 plus y1. And that give me cx1 plus cy1. So this is true. So that means cu belongs to w. That means w is a subspace. Second question, the set is what? AB, so that the first component is a negative. The first component, this is not a subspace. For example, let u minus 1, 2, and 3. This belongs to w, since the first component is negative. But minus 2u will be what? 2 minus 4 minus 6. This does not belong to w. Since now this component becomes positive, I multiply by a negative value. So it means w is not a subspace. Okay. Yeah. Now this is what happened in 4.2. Now we extend this idea for different functions or different ideas. Like here I have it in R4. The same thing, huh? We'll do the same thing. But now I have R4, R5, Rn. Who cares, huh? So I have such examples. Okay. And also I can extend it to sometimes to general statements. Okay. He said determine what is this set? This set is the set of all vectors whose coordinates satisfying this single homogeneous linear equation. So this is single homogeneous. What they mean by homogeneous? Not the homogeneous in 1.6. Huh? Homogeneous here as for the linear equations, the right hand side is equal to 0. This is they call it homogeneous equation. So this equation, I have n unknowns. I have only one equation. It means I have infinitely many solutions. So if you collect all of these infinitely many solutions, I put them in a set. And is this set a subspace or not? And it is a subspace. So these are the vectors. So I will let u, if u, which is x1, x2, up to xn, let me use x1, x2, xn, like the way he's doing it. If this belongs to w, that means what? That means this vector satisfies this equation. So it means a1, x1 plus a2 plus an xn equals 0. By the way, the a's are fixed, huh? Are fixed a's. Okay. Now, if v y1, y2, yn belongs to w, that means it also satisfy the condition. So we have a1, y1 plus a2, y2 plus an, yn is equal to 0. Now the question is u plus v belongs to w or not? And it is. Why? Because u plus v is what? x1 plus y1, x2 plus y2, xn plus yn. So the question is a1 times the first component plus a2 times the second component plus an times the last component. Is that equal to 0 or not? So this is the question. Would that be equal to 0? So we'll start with this one. I have a1 x1 plus y1 plus a2 x2 plus y2 an xn plus yn. That I can rewrite it. I can write the x's in one, a1 x1 plus a2 x2 plus an xn, and then write the things with the y's. And I know that since this is a vector in W, that means satisfy this. So all of this is 0, and this is 0. So that will be 0 plus 0, which is 0. So that means this vector u plus v belongs to W. Now I need to check the second one. Is cu belongs to W? Do the same thing. Cu is what? Cx1, Cx2, up to Cxn. So the question is Cx1 plus Cx2 plus Cx1 is equal to 0. And this is true. Yeah, you can see it from here. If I took C as a common factor, no, sorry. C, the question is A1 Cx1 plus A2 Cx2 plus an Cxn. This is equal to 0 or not? Yeah. If you notice what a1 Cx1 plus a2 Cx2 plus an Cxn, that will be what? I can take C common factor. The remaining is this, which I know is 0. So I have C times 0, which is 0. So that means Cu belongs to W. That means W is a subspace. Yeah, this is what we did in 4.2. Just we expand this subspace idea to Rn. Yeah, this is took it in general, but now we'll deal with example, like what we did before. Now I have this set W will be x1, x2, x3, x4, so that the first component or all components are non-negative. x1, x2, x3, x4 are non-negative. Is this subspace or not? By the way, in this case, the first condition, which is the sum, if I add it, still the components will be non-negative. However, my problem is in the second condition, the scalar multiplication. The first condition will work. You have no problem with it. It will satisfy. It will, but to show it's not a subspace, I need only one example, either from each condition. So I let U equal 1, 1, 1, 1. This belongs to W. However, multiply by -2, for example, or -1, who cares? -2, -2, -2. This for sure does not belongs to W. So W is not a subspace. W is not a subspace. Okay. Yeah. Determine this set. X1, X4 is equal to 0. So I have this set where the first component times the fourth component, you multiply them I'm getting 0. Is this set a subspace or not? Oh, check. Yeah, I think that it's not. Why? Let U, for example, 0, 1, 2, and 3. So 0 times 3 is 0. So this is belongs to W. And let V 1, 2, 3, 0. So still satisfy. This also belongs to W. But U plus V will be what? 1, 3, 5, 3. I don't care about these things. We care about this. Now, this times this is not 0. So this does not belong to W. So W is not a subspace. W is not a subspace. And I think the scalar multiplication will work. But this one will not work. Okay. Show that is a subspace. Yeah. So let U x1, x2, x3, x4 belongs to W. That means x1 plus x2 plus x3 plus x4 is equal to 0. That's what they have. If you add these components, I'm getting zeros. The next one, I let V y1, y2, y3, y4 belongs to W. That means I have y1 plus y2 plus y3 plus y4 is equal to 0. So I need to check U plus V belongs to W or not. To do that, U plus V will be what? X1 plus Y1, X2 plus Y2, X3 plus Y3, X4 plus Y4. So if I add these things, add these components, I'm getting 0 or not? That's the question. And it is. If I combine the x's, which I know they are zeros, and I combine the y's, which I know they are zeros, I have 0 plus 0, which is 0. So this is true. So this is correct. SCU belongs to W. Yeah. This idea. What is CU? It will be CX1, CX2, CX3, CX4. So the question is CX1 plus CX2 plus CX3 plus CX4 is equal to 0? And it is, since if we take C common factor. Yeah, this is very clear to see. I have C times 0, which is 0. Okay. That's it. So it is yes. So W is a subspace. W is a subspace. As I said, in R2, in 4.2, we don't have new things, just we have extension of this idea of subspace. I think this is not a subspace, easy to do, like what we did here. Now it's almost the same. So I have the U, and the first one to be 0, 1, 2, 3, 4, who cares? This belongs to W. Now I have R5, which is actually the same idea. So this belongs to W because x1 times x2 is 0. Now let V, the opposite, 1, 0, 2, 3, 4, who cares? Belongs to W. Now it's still 0, but U plus V, which is 1, 1, 4, 6, 8. This does not belong to W. I care only about these two, since the product is not 0. So W is not a subspace. W is not a subspace. Determine W is not is a vector or not. I have x1 equal 3x3 and x2 equal 4x4. Is this subspace or not? Yeah, I think it is a subspace. Let me show you that they are subspace. Oh, yeah. What happened in this one? I have what? W. Let me rewrite the x1, x2, x3, x4. So that what? x1 is 3x3 and x2 is 4x4. That will be the set. I think it is subspace. Let me try to prove it. Let u x1, x2, x3, x4 belongs to W. That means I have this. Let V y1, y2, y3, y4 belongs to W. That means what? The first component equal 3, the third component, and the second component equal 4 times the fourth component. Now, I need to check is U plus V belongs to W or not. So do this. U plus V is what? X1 plus Y1, X2 plus Y2, X3 plus Y3, X4 plus Y4. I need to check now is the first component is the same as the third component or not? It's the same as 3 times the third component. So I need to check in x1 plus y1, is it equal 3, x3 plus y3? That's the first question. And the second question, I need this, the second component, yeah, x2 plus y2, is it the same as 4, the fourth component? That's the question. And this is true. Why? If you notice, yeah, x1 plus y1 will be x1 is 3x3, so that will be 3x3 plus 3y3. I can take 3 common factor, which what I'm looking for. So this is true. And the same thing here, x2 plus y2, it will be 4, x4 plus 4, y to the power y4. So we have 4, x4 plus y4. What means this true? And the same thing, I think I can easily check for CU. I will leave it for you. I can let me do it. We'll complete this C1, CX2, CX3, CX4. So I need CX1 equals 3 CX3, which is very clear true. And CX2 equal 4 CX4. And this is also true. So CU belongs to W. So W is a subspace. Yeah. Now it's R2. Okay. Is it subspace or not? Hmm. Yeah, it is subspace. It's not. It's not subspace. Yeah, I can do this. Like, let u 1 and 0, which belongs to the value, since 1 square plus 0 square is equal to 1. Let v 0 and 1. This belongs to the value, since 0 square plus 1 square is equal to 1. What will be u plus v? U plus v will 1 and 1. And this does not belong to the value. Since 1 square plus 1 square, this cannot be equal to 1. So W is not a subspace. Okay. Now we move to this idea. Um, Yeah, which is the second part in this in 4.2 exactly. Um, the idea is not that difficult. The idea is I mean we need to deal with this theorem. We're saying what? If you have a constant matrix m by n matrix, then the solution set of the homogeneous linear system is the subspace of Rn. Okay, you know, if you have m by n, especially if m is greater than n, then it means if n represents the number of variables. So if you have the number of variables, if m is less than n, if the number of variables is for a homogeneous equation, like this one, homogeneous equation. Let me see something here. Where is it? Yeah, like this one. I have only one equation with n variables. For sure, I have infinitely many. So if the number of variables for homogeneous equation, if the number of variables is more than the number of equations, then I have infinitely many solutions. Okay. Now he's saying what? If I want to solve such system, x equals 0, where I have the number of variable, I mean the x values, the x vector, this is just a vector in Rn, will give me infinitely many solutions. If I collect all of these x values, x vectors, I put it in a set, then that set is a subspace. So you can prove it easily. Let me just sketch the proof. If x1 belongs to this set W, huh? So W is what? W, all x belongs to Rn, such that ax equals 0. If I multiply that vector by A, by the matrix, I am getting 0, which is the A is a fixed matrix, n by n matrix. Okay, x1 belongs to W means ax1 equals 0. x2 belongs to W, that means ax2 equals 0. Now we can check x1 plus x2 for sure belongs to W. Or let me say, how to check x1 plus x2 belongs to W. It means I need to check x1 plus x2 is equal to 0, and that is true, very clear, because it will be ax1 plus ax2. And the same thing for cx1 belongs to W. Since I have cx1, this will be 0, since I can't take the c outside. So this is actually what it says, the theorem. So the solution set of the homogeneous linear system is subspace. And not only that, now in this question, in this example, I want to find a way, since it's a subspace, means it can be generated by Rn. So it can be generated by a specific number of vectors. I need to find those vectors which generate the solution space, this solution space. Okay, so I need to find two solution vectors so that the solution space is the set of all linear combinations of these two. So any solution of this system can be generated by U and V. I need to find these two vectors. There is a procedure. I will tell you the procedure. What we will do, I will rewrite this as a system. So I have what? 1 minus 4, 1 minus 4, 1, 2, 1, 8, 1, 1, 1, 6 times x1, x2, x3, x4. That should be equal 0, 0, 0. I write it to make it ready as a Gaussian elimination, augmented matrix, like what we did in chapter 4, in chapter 3, I mean. 1, 2, 1, 8, 1, 1, 1, 6. Yeah, and this is 0, 0. Actually, this will not be changed 0, 0, because, okay. So I need to make this zeros. You know this Gaussian elimination step. So let me just make it smaller. So I have more space. This is 0, 0, 0. That will not be affected. That will be 0. Multiply by -1 and add, that will be 6. Multiply by -1 and add, that will be 0. By -1 and add, that will be 12. Multiply by -1 and add, that will be 0. Multiply by -1 and add, that will be 5. 0. That will be 10. Also, I can get rid. Yeah, if you want me to write the steps, I say minus R1 plus R2 minus R1 plus R3. Okay, now multiply 1 over 6 R2, 1 over 5 R3. That gives me what? 1 minus 4. 1 minus 4, 0, 0, 1, 0, 2, 0, 1, 0, 2, 0, 0. Okay. So also I can get rid of the third row. Multiply minus R2 added to R3. So I have what this is I will not change it. This one will be 0, 1, 0, 2, 0, 0. Multiply by -1 and add, that will be 0, 0, 0. So the last row will be gone. So now I have this system, which I can make it again. I can return it back as an equation to see how we can solve it using the back substitution. This one is easy one. X2 plus 2x4 is equal to 0. Okay, let me tell you the idea. You need to distinguish about two things. After writing this in row reduced echelon form, writing the matrix, you need to do what? Do it this way. Go to the first row. I need the first element, which is non-zero, or 1. Yeah, since I make it 1. So it will be this one. Go to second row. The first element non-zero is this one. Don't forget, this is x1, this is x3, x2, this is x3, this is x4. That means what? Since this one is with x1, this one with x2, that means x1 and x2 called leading variables. I don't have other ones. And the rest are called free variables. When I say they are free variables, means those will be I can choose them. I can choose any value for those free variables. So I let x3 to be t and x4 to be s. Okay. Now I need to rewrite this solution. I need to write this system in terms of x3 and x4. Look, I have two equations, so I could have two answers. So now I need to write it in terms of these free variables. It's very clear. I have x2 is minus 2x4, which is minus 2s, since s is x4. And from here, I have x1 is what? 4x2 minus x3 plus 4x4. Now I put s and t. I have what? x2 is minus 2s, so that will be minus 8s. x3 is t. This is 4s. So the answer is minus t minus 4s. So this will be x1. And this will be x2. So now if I write the solution, x1, x2, x3, x4, what I will get? x1 is what? Minus t minus 4s. x2 minus 2s. x3 t. x4 s. Now I will take t from the first one. or I can rewrite it as minus t 0, then t 0, and down with the s, which is minus 4s, minus 2s, 0, and s, where I can rewrite it, and now I can take t outside here. I have minus 1, 0, 1, 0. If I took s, I have minus 4, minus 2, 0, 1. That will lead us to what? Note I want to have t times the vector and s times the vector. So I can call this v, and I can call this u. So the two vectors are what? U, which is minus 4, minus 2, 0, 1. You can write this u and v, it's okay. And v, but since I'm saying tv and su, maybe I should use s and t instead of t and s. It's okay. These are just names. So v equals minus 1, 0, 1, 0. So these are the two vectors which generate all solutions for this system. So any solution, that means what? Any solution. Now I wrote any solution. Huh? This is what they dealt with the general solution. I'm solving this system. I'm finding the general solution, which is this one, and I wrote it in terms of these two vectors. So any solution of this system can be written as a linear combination of these two. And this is the procedure. You do the Gaussian elimination until you reach this one, where you distinguish between the leading variables and the free variables. Then, if I have the free variables, I can write it in terms of, I put it in terms of anything. Yeah. Okay, let me do more examples about this idea, and then I will stop. Okay, the same thing. So this is the system. 1 minus 2, 3, 2, 1, 0, 2 minus 4, 8, 3, 10, 0, 3 minus 6, 10, 6, 5, 0. Yeah, need more space. Okay, so what I will do, let me do the calculations quickly. Multiply by minus 2 and add, that will be 0. By minus 2 and add, that will be also 0. By minus 2 and add, that will be 2. By minus 2 and add, by minus 2 and add, that will be minus 1. By minus 2 and add, that will be 8. By minus 3 and add, that will be 0. By minus 3 and add, that will be 0. By minus 3 and add, that will be 1. Correct? Minus 3 and add, that will be 1. Minus 3 and add, that will be 0. Minus 3 and add, that will be 2. Okay. Yeah. So to make it easier, I can interchange this row with this row. So I have 1 in this one. So I have what? 1 minus 2, 3, 2, 1, 0, 0, 1, 0, 2. They have 0, 0, 2, minus 1, and 8. So now we'll do the same trick. 1 minus 2, 3, 2, 1. This is 0, 0, 1, 0, 2. Multiply by minus 2 and add to the second. Yeah, let me write what I'm doing. Minus 2 R1 plus R2 minus 3 R1 plus R3. Interchanging R1 with R2 with R3. This one, yeah, multiply R2 minus 2 and add it to R3. So this is will be 0. That will be minus 1. Multiply by minus 2 and add it, that will be 4. Okay. So I'm getting this. Now I stop. Now we'll do this idea of free variables. Okay. So the first element here, zero or one, it will be this. The second row, no. Also, you know, I can do it. I forget one second. Yeah. Yeah, I can continue. Sorry. I shall continue. Yeah, since I have still here. So you can multiply the last one by minus R3 to get this. 1 minus 2, 3, 2, 1, 0, 0, and 0, 2, 0, 0. I want one. Usually it's better to have it as one. Okay. So now I will do this. Uh, yeah, the green things. Okay. So I have one here, one there, one there. This is the first element about the rows. Don't forget this is x1, x2, x3, x4, x5. So what are the leading variables? They are x1, x3, x4. What are the free variables? X2 and x5. So I let x2 equal t and x5 equals s. Now I need to write the solutions, the remaining solutions, which is x1, x3, x4, in terms of these x2 and x5. So let me return it back to the equations. x1 minus 2x2 plus 3x3 plus 2x4 plus x5 is equal to 0. This is the first equation. Second equation is what? x3 plus 2x5 is equal to 0. By the way, I don't need 0, 0, 0 because it's will make no difference. Huh? Yeah, since it's 0, 0, 0, it's not like non-zero numbers. And also I have x4 minus 4x5 is equal to 0. Very clear from here. I'm getting that x3 minus 2x5, which is minus 2s. And from here, I'm getting x4 is 4x5, which is 4s. And from here, this one, I'm getting x1. Yeah, I need to be careful. 2x2 minus 3x3 minus 2x4 minus x5. Yeah, if we do the calculation, I want to write in terms of t and s. T is x2, so it will be 2t. Yeah, s is the remaining. I have minus 3x3 times minus 2, that will be 6s. 6s minus 8, that will be minus 2 minus s, so it will be minus 3s. Okay. Now, so this is x1, is this one. X3 is this one. X4 is this one. And this is x2, this is x5. So I write the solution. Now in terms of s and t, so I can take common factors. X1 is 2t minus 3s. X2 is t. X3 is minus 2s. X4 is 4s. X5 is s. So I take the t outside. I have what? 2, 1, 0, 0, 0. And if we took the s outside, I have what? Minus 3, 0, minus 2, 4, 1. So what will happen? This will be v or u, and this will be u. So the two vectors are these two vectors, u minus 3, 0, minus 2, 4, and 1, and V 2, 1, 0, 0, 0. Okay. Let me do these two quickly. Yeah, the same thing. I need to find U and V. Sometimes, by the way, it's only not only one vector. Sometimes they are not always two vectors. Huh? Sometimes they have only one vector. Yeah. But all of these examples, I have two vectors. Later, we'll do examples where I have only one vector. Just you need to see the solution of the system. So I have 1, 3, minus 15, 7. I don't need 0, 0 because it's 0, 0, 1, 4, minus 19, 10. Well, this is what I mean, 0, 0, because multiplying by 0, 0 all the way, so that will not do any change. 5 minus 26, 11. So let me do it. Yeah, let me do it quickly. Yeah, why not? Specify the steps. Minus R1 plus R2, minus 2R1 plus R3. See what will happen. That will be 0. Minus 3 plus that will be 1. Minus 3. What do you mean minus 3? Minus right away. Minus 15, that will be minus 4. Minus 7, that will be 3. Okay. Times minus 2 and add, that will be 0. Minus 2 times, that will be minus 1. Minus 2, that will be 30, that will be 4. Minus 2, that will be minus 3. Okay. Now I need to use this with this to get rid. Now it's ready. No need to do an interchange or anything. Minus R2 plus R2 plus R3. Just add them. 1, 3 minus. Multiply the first one by 1 and add it to the second one. That gives me 0, 0, 0, 0. Okay. So if we do this trick about the free, these are the leading. So we have leading variables. These are x1, x2, x3, x4. Leading variables, x1 and x2. The free variables, those what I'm looking for, x3 and x4. So I call it T x3 and S x4. And I write x1 and x2 in terms of T and S, or in terms of x3 and x4. So I have what? The equations, x1 plus 3x2 minus 15 x3 plus 7 x4 is equal to 0. This first equation. Second equation, x2 minus 4 x3 plus 3 x4 is equal to 0. So from here, I'm getting x2 is 4x3 minus 3x4, which I can write in terms of S and T, 4t minus 3s. And from here, I have x1 is minus 3x2 plus 15x3 minus 7x4. Just the thing becomes a little bit complicated. Minus 3 times this, that will be minus 12t plus 9s plus 15t minus 7s. That give me what? 3t plus 2s. So my solution, x1, x2, x3, x4 will be what? x1, which is 3t plus 2s, is x2, which is 4t minus 3s, and they have t and s. Take t outside. Take the common factor, I have 3, 4, 1, 0. Take s common factor, I have 2 minus 3, 0, 1. So those are the vectors I'm looking for. 3, 4, 1, 0, and 2 minus 3. So this will be, so this is my U, and this is my V. Call it T and S. Yeah, no, he's using U and V the other way, no problem. So this is U. I need two vectors, who cares? What is U, what is V? So these are the vectors which generate the solution space. Yeah. Let me do the last one. 1, 4, 1. Actually, it's the same as the first one. Yeah, so no need to do it. Yeah, it's the same. Okay, which is the same as this one. Yeah, the same idea actually. I will stop here. Later I will do. Now these are the main ideas in these two sections, which is just to say it again. What we have in these two sections, I have let me just quickly say what we have in these two sections, and then we'll try to do problems. We talk about the vector space, R2, R3, Rn. These are the same. How to add them, how to multiply them, how to find the length of the vector. And then we talk about linear independent. And we have the general definition, which is writing it as a linear combination equal to 0. The linear combination equal to 0. I need to say if I have A, B, C, all are zeros, these are the only possibility, then the three vectors are linear independent. 2 vectors, 3 vectors, the same idea. 10 vectors, the same idea. If there is at least one, not all zeros, if there is one, either A, B, C, or all of them are not zeros, then they will say they are linear independent. And also we can use it, you can use the determinant to do that. Not only that, also, if the vectors are linearly independent, 3 vectors in R3 linearly independent, then they constitute a basis for R3. And also we define what's called linear combination. What do you mean? The W is a linear combination if it's written as a linear combination. If there exists scalars A and B, says that AU plus BV is equal to W, and we did questions how we can express a vector as a linear combination with other vectors. Then we move to the like these questions just to show you they are dependent or independent, either by finding A, B, C not 0 to show that they are independent, or also we can to show they are dependent if A, B, C are not zeros. If A, B, C all are zeros, then they are independent. Also, we can use the determinant to do that. And if they have 3 vectors in R3 and they are linearly independent, then for sure they form a basis. That also how we can write T as a linear combination with the other. This is what we did in all of these problems. Then we talk about subspace. What we care about, if I have a subset, we care about these two conditions. The subset, is it closed under addition and closed under scalar multiplication? And we did many examples. In 4.2, what he did, he extend that idea instead of R2, R3 to R4, Rn. Actually, it's the same idea. So yeah, and also can extend it to any collection of things. And then the last things we did in 4.2 is how to, if you have solution space of solution space of a system AX equal 0, how to find how to find vectors that can generate that solution space. And I think we did 3 examples. I think they are that enough. This is what we did. This is what we have actually in these sections, 4.1, 4.2. Later I will do some problems from some exam from the old exams. Yeah. So let me stop now. Stop the recording. Thank you.